So our next speaker is Susanne Wiesner from the University of Wisconsin. Susanne, are you able to share your screen? Excellent. And so, yeah, take it away when you're ready.
Yeah, so while this is not a team talk, it's certainly a team effort looking at this research. So this is the team between the USDA Dairy Forage Research Center, Stefan Metzger from NEON, and then of course Ankur Desai and Paul Stoy from UW-Madison. Oops. So you've seen this or more of this graph today earlier in Caroline's talk already. I wanted to put this up and not to talk about natural climate solutions in particular, but every time I look at this graph, I look at the error bars. And that's really the motivation for this research that I'm presenting today, trying to come up with solutions that account for this uncertainty and decrease the uncertainty in terms of natural climate solutions. So to do this, we are working in a farm system. So this is the Dairy Forage Research Center farm by Prairie du Sac, Wisconsin. This is a working dairy farm with a herd size of approximately 700 dairy cows and heifers. And as you can see, the farm grows a variety of different crops, which are mainly grown to feed the cows, which are alfalfa, corn, soybeans, wheat. And you can also see that a large proportion of this farm is comprised of vegetation like forests, grasslands, and shrublands. And the star there indicates the location of the Meriflux Tower USDFC, which is a 30-meter tall tower. So a challenge with that tower was, of course, to calculate the fluxes because most eddy covariance assumptions would not apply in this case for one having a homogeneous surface. So our main objective for this research here were really to see if the environmental response functions approach that Stefan Metzger developed can be applied in heterogeneous landscapes like this. And second, if we can use the results from those to improve remote sensing models. And this is really important in agricultural systems because crops are continuously being modified genetically or through breeding programs. So to really capture if it impacts the physiology or carbon uptake potential of these crops, I think having something like this in place is really important. No, it always goes back. Bear with me with the slide because it's gonna get a little bit busy, but I wanna just talk you through the methods that we applied. So the first step was actually to use two remote sensing models, the GPP model developed by Zhao in 2004, and then the ecosystem respiration model developed by Gao in 2015. And these models use, in this case, Landsat data for enhanced vegetation index, land surface water index, and land surface temperature. PPFD, so photosynthetic active radiation, as well as maximum quantum yield, which is basically the amount of carbon a certain crop species can take up per amount of photosynthetic active radiation received. And this is really the parameter we thought we wanted to improve using eddy covariance. So the ERF, the environmental response functions approach, basically uses high frequency eddy covariance data as well as spatial information of the landscape. So in this case, land surface temperature and enhanced vegetation index. And it quantifies the contribution of each vegetation type through footprint characteristics. And all of this then is fed into a machine learning approach so that we can extrapolate the CO2 fluxes onto the landscape. So the picture on the down left there, you can see is basically 1 hour of CO2 fluxes. And we did this for all hours in 2019. So I got a time series, a spatial temporal time series for the year of 2019. And what we did then was extract the NEE fluxes for each of the different fields as well as vegetation types. So in the end, I actually had about 70 different NEE time series from that ERF approach. I fed these through REDPROC to filter and get full the data. And then I used that data from all the fields and all the different vegetation types to estimate the maximum quantum yield from the light response curves. So in the third step, then we fed that back into the remote sensing model and then quantified how all of these three different approaches compare to harvest data. So the great thing about this farm, and probably other farms as well, they have a lot of data, and we have all the harvest data from each individual field. So we compared the remote sensing results as well as the ERF results to that. And I'll show you that in a second. So in this graph, you see the daily carbon fluxes in megagrams of CO2 per day. And this is because in the paper, we're actually comparing this to the emissions from the farm as well. And I'm showing you 4 different time series here too. One is the remote sensing model that used literature maximum quantum yield data. In a lighter green, you see ERF, which is the total environmental response function results. ERF MQY is the improved remote sensing model using the ERF maximum quantum yield data. And then you see in red there, ERF day. And this is because when I first plotted this graph, I didn't include the ERF day yet because I just looked at the comparison to the remote sensing model and the eddy covariance data. And I thought, well, that didn't work. But then I realized, of course, remote sensing, or at least the remote sensing models I've been using, are only fed data from the daytime. So we're using photosynthetic active radiation from the day, and then the Landsat data, the reflectance data, has been taken during the day. So I went back to the ERF and basically just extracted the daytime NEE data. And sure enough, after that, it really correlated well with the remote sensing model as well, which I think is an interesting result from this too, showing that at least the remote sensing models I've been using are basically underestimating total ecosystem respiration. And then just to sum it up in a simple graph. So again, I told you I compared these data to the harvest data. So what you see here in the bar graph is basically are the regression coefficients between the remote sensing model using literature maximum quantum yield in the center ERF for each field, and then the improved model. You can see the remote sensing model already worked pretty well. ERF is just right at the same slope as well. So it's predicting the amount of carbon pretty well too. The fit is a little bit better. And then you see the improved models actually, we see an improvement as well. So I think that is really, I can't think of the word now, but it was a good result. And then to just show you how that looks like just in a comparison of the improved model. So here MPP, ECH, sorry, I didn't change that. That is the ERF MQY, so the improved model using the ERF maximum quantum yields on the x-axis, and then on the y-axis we have the total harvest net primary productivity. And each of these dots are one field at the farm. So you can see that it works pretty well for the individual crop types as well. So to conclude, for our first objective, can we use eddy covariance to monitor natural climate solutions? Using the ERF approach and while accounting for the complexity of the landscapes, I would say, yes, we can. And can we use eddy covariance to improve remote sensing models to upscale natural climate solutions? Yes, we can. And lastly, I think an important point is at least the models that I've been using, the remote sensing models, underestimated total ecosystem respiration. So, and the environmental response function approach has the advantage of really allowing us to monitor the ecosystems at night as well. And with that, I hope it wasn't too fast. Thanks for all my funding sources for the Dairy Innovation Hub, my collaborators, my co-authors, and thanks for listening.
Super. Thank you so much, Susanne. I think